Okay, um, today's lecture we will continue where we left last time and discuss further about Reynolds stresses and how to compute them in terms of what is called an eddy viscosity. And then we will see how what does eddy viscosity depend on, and it turns out that we have to define certain length and time and velocity scales of turbulent motion to obtain the eddy viscosity. Okay, Reynolds stresses we defined as tau ij as minus of u prime I u prime j. For a three-dimensional flow, this will give us a 9 by 9 stress tensor, Reynolds stress tensor. Many times there are 6 independent Reynolds stresses. So if you want to compute a turbulent flow and get the mean velocity profile, in a general 3D flow, you will actually have to get values for all these Reynolds stresses, which depend on fluctuations, so we cannot directly compute them. These are unknowns. These are like non-closed terms in the momentum equation. But what we know about these is that physically they represent turbulent mixing. They represent diffusive effect of turbulent mixing, and in many ways they are similar or analogous to viscous stresses. Okay, so people have proposed formulas to calculate tau ij, which are very similar to what we already know for the viscous stress tensor. So let me write that down first. Sigma ij we know as mu, a viscosity, times dui dxj plus duj dxi minus 2/3 mu, the dilatation or divergence of velocity, written in tensor form as duk dxk. K is a repeated index, so it's a summation over 3 derivatives times delta ij. Viscosity, the dynamic viscosity mu, here represents the effect of molecular random motion on diffusing properties of a flow, which the property could be like momentum in this case, from a region of high momentum to low momentum. So the similar action is done by the Reynolds stresses, and we define a similar quantity called eddy viscosity or the turbulent viscosity, and write an expression for tau ij as mu t times dui dxj, exactly similar to the viscous stress, minus 2/3, again mu t instead of mu, and the dilatation, divergence of velocity. Now these are defined in terms of mean velocity, u bar everywhere, which means that if you're computing the Reynolds averaged Navier-Stokes equation to get the mean flow, these u bar and the derivatives will be known as part of the solution. So we can compute tau ij if we know the eddy viscosity mu t. So from 6 or 9 tau ij's which were unknown, now we're down to one quantity which is mu t, eddy viscosity. There are a few properties of tau ij that we need to know before we move on to see how to compute eddy viscosity. One is in a boundary layer, turbulent boundary layer, the main Reynolds stress is tau xy, which is minus u prime v prime bar. And if you apply this formula, we get mu t times I is 1, j is 2. So we get mu du bar dy. And let's assume that it is an incompressible flow. So the divergence of velocity is identically 0. In a boundary layer, we know that the main velocity gradient that we have is the wall normal gradient du bar ddy of u bar. We also know that u increases with y, so this quantity is greater than 0. In a turbulent flow, it is when we measure u prime v prime and we calculate this quantity, the average of this product, it turns out that this quantity is negative. There is physical interpretation for this. We will not go into it at this point. It's a bit advanced. But if you measure it, and people have reported in many different experiments on turbulent boundary layer, and they have found it to be negative. So the term tau xy is actually positive. Du dy is greater than 0. So eddy viscosity has to be greater than 0, and that is absolutely consistent with what we know of what we expect of eddy viscosity. Like molecular viscosity can never be negative, so eddy viscosity also cannot be negative. So this is the basic idea on which Reynolds stress and its modeling via mu t is based. But there are other situations where this assumption does not hold. One simple case is, let's say we have tau xx. It will be mu t. Before that, let me write tau xx as minus u prime square bar. This will be mu t times du bar dx. Now, in a flow, okay, let's look at the left hand side first. U prime square is a square of a quantity. It has to always be positive. So, tau xx is actually negative, and if du dx is positive, then we will have a situation where mu t is less than 0. Naturally, it's a contradiction of what we would expect for mu t to do as a effect of mixing and viscosity. So we have to keep in mind that this formula is not always valid. It works well for turbulent boundary layers, canonical flows, simple, well-studied flows like boundary layers, free shear layer, wakes, and so on and so forth. It does not work in many other situations, and one particular case is shock waves. So we will see how that comes up at a later stage. Okay, knowing that, let's move on to see how to compute eddy viscosity. Okay, here we again go back to the picture which shows the analogy between turbulent mixing and molecular mixing. We show that we are looking at a part of a boundary layer which has a velocity gradient of this kind. And the velocity gradient is du dy. We had drawn a picture of this kind where across any imaginary hypothetical plane, molecular mixing will have random molecular motion which can transfer momentum from the low velocity side of that to the high velocity side across an imaginary plane. We said this is effect of molecular diffusion. We defined as sigma xy, which is mu times du dy. Once again, in a boundary layer kind of scenario, du dy is the main velocity gradient, and this is the main viscous stress. We drew an analogy with turbulent mixing across again another hypothetical plane. We said there are lot of eddies which are mixing the fluid up, down in any random way, and this effect of this mixing tau x is represented by tau xy, and it is mu t times du bar dy. Okay, now molecular viscosity, we know it's a function of temperature, but physically, if you go into the details of kinetic theory of gases, where the molecular motion is studied, we can show that molecular viscosity is, it's not equality, but it's like proportionality, let's say, or is proportional to the density of the fluid. Higher the density, more the molecules which can exchange it. It depends on the velocity of the random motion. It's called the thermal velocity, which is the Brownian motion, and it's a function of temperature, and that's what brings the temperature dependence of mu, and times lambda, which is the mean free path of the molecules. How far the molecules go before they collide again tells us how much of mixing they can do. Higher the distance they go, the more of the mixing. So viscosity represents the effect of mixing, and it is proportional to rho, a characteristic velocity of the molecules, and a characteristic length scale, which is mean free path for molecular motion. We use the same analogy to define turbulent or eddy viscosity proportional to rho, similar to the one above. A velocity that is now characteristic of the turbulent eddies or mixing, which is doing which is the effect that mu t is trying to capture, and then a length scale which is also representative of the turbulent mixing. Okay, so now the problem comes down to how we can get these values of turbulent, a characteristic scale of turbulent velocity fluctuations, u prime. We know u prime, v prime, w prime exist, but what about what can be one number that we can use to get eddy viscosity? And we will show that one way to do is take an average of all three directions. To do that, we will actually define what's called turbulent kinetic energy. Which is defined as half u prime square v prime square w prime square, and it's an average quantity. You average it up, and it's a sum of averages, so we can define it will be the sum average of sums, so it's sum of averages. This is defined as K, turbulent kinetic energy. It's very similar to any kinetic energy we define using velocities, but it's defined per unit mass. So that's where the rho or mass m does not come in. If you think about this quantity, half of u prime square, v prime square, w prime square, it's also like the resultant velocity that you can get from at any point. So let's look at what is the velocity scale of turbulence. And here we come to the third part of the lecture, where we say velocity scale V turbulent equal to, or does not, it's not always equal, it's somewhat proportional or similar to u prime square v prime square w prime square. Imagine that you have u, v and w primes in the three directions. How would you find the resultant? You would take the squares, sum them and take a square root. And because everything is varying in time and fluctuating, we will take a bar of it so that we get a reasonable thing to handle. So this is a way of defining one single velocity fluctuation or a characteristic velocity instead of three different directions, only one number which represents the three directions together as the velocity fluctuation at a given point. And this turns out to be twice of k and a square root as per the definition of turbulent kinetic energy we have defined. So turbulent kinetic energy, if you know, you can actually get the velocity scale, the characteristic velocity at a given point. And turbulent kinetic energy varies from point to point in the flow, so you will get a variation of or know how the local turbulence behaves. The other thing is a length scale, which is a little bit more difficult to obtain. Here there are many different propositions. The length scale of turbulence, for example, if you think of a flat plate boundary layer of this kind, I'm showing only some part of the boundary layer, not from the tip of the plate. And we can think of that there are turbulent vortices, eddies as they're called, fluctuations, mixing. They're small, big, medium, all different kind of eddies. An assumption or approximation is that the largest eddies there can be are of the size of the boundary layer itself, the thickness of the boundary layer. So if I call this as delta, L turbulent is kind of proportional to delta. Of course, cannot exceed delta. Turbulence is all inside the boundary layer, but it's of the order of delta. This symbol, which I write as tilde, is something like similar to, of the same order and magnitude as this. So this gives us an estimate of, if you know the turbulent boundary layer thickness, you can actually make an estimate of L turbulent, length scale of turbulence, put it back into eddy viscosity, and then that gives you Reynolds stresses, and you can compute the velocity profile, mean velocity profile. But then how would you calculate the mean velocity profile or the boundary layer thickness delta, which actually comes from mean velocity profile before calculating the mean velocity profile, mean velocity? So it's not a very easy thing to do. You have to make an approximation, try it out, and then maybe correct it if you wish. But there are a number of models, turbulence models, which are based on an idea of a length scale, which is thickness of the boundary layer, thickness of a free shear layer where there is turbulence, and so on. The other thing that goes into such a model is that the scales of turbulence, the eddy sizes of eddies are not same everywhere in the boundary layer. As you go closer to the wall, somehow the scales become smaller and smaller. So in fact, there is a proposal models. There are assumptions which say that it will be proportional to distance from the wall. Okay, and there will be, of course, a proportionality constant, and so on and so forth. So length scale is a very tricky thing to compute or obtain in a turbulent obtain a priori before you compute the flow. To get to the estimate of the length scale is not easy, and these are some forms of turbulence models. Of course, there are many more. You put in certain constants and you put in certain empirical formula functions in there to make it work, but these are something of the sort of algebraic turbulence model. They are called algebraic turbulence models, which still allow you to actually way to compute the eddy viscosity and then put it into the Reynolds stress, and then close the equation of mean flow or the Reynolds average RANS equations, and then you can actually get a solution for a turbulent boundary layer. Once you get a solution, it will not be right, so you compare with experimental data and you try to fine tune your assumptions in such a way that you get the correct answer, and you hope that the same thing will apply next time in the next experiment that you compare with. Okay, so with that, I will kind of stop here and pick it up next time to tell you more about more advanced turbulence models which do not depend on certain conditions, as I'm